We are live.
Yep, now we are. Well, from the web perspective, we are about 20 seconds behind real time.
That's even better than live on TV.
Is it? So-called live TV is
Always delayed.
by how much? Is it for legal
At
reasons
5
so
seconds.
they can beep out
So
stuff?
that's exactly why it's delayed.
So
Something they don't wanna-
legally-
they don't, so it doesn't get sued for something that.
Someone said.
Exactly.
Yep, exactly.
But then you can
Or
sue them.
shown.
But you can sue them now that what they claim to be live is not live.
Right.
Hasn't been live for a long time.
That's a
It's
whole
all
other
one
can of
take.
worms.
Yes. Okay. All right. So we'll get started today with. Well, the homework assignment or tonight's lab activity is going to be a little bit intense, in the sense that you would need to understand all the material from before, including conditional branches. So so what we'll do today is we're going to go through some examples with conditional branches or branching in general. Okay, so we'll go through some loops and we'll go through some techniques of how do I know whether my code is working or not. Okay, so is that okay? Okay, all right, so let's go ahead and do that. And on top of that, we also can start to introduce a new module in terms of reading assignment, what you can read to help your programming. So we're basically transitioning into the third large chunk of modules. So we are basically getting to compiling C control structures at this point, which is kind of cool because now we have all the basic pieces and we are now putting the basic pieces together in order to implement high-level programming concepts that we already know from cisp 360. Okay, so let me just kind of click on this one to show you what it looks like. Tonight's lecture is not going to be coming from here, but instead it's just doing stuff by hand. So basically, when you look at this thing here, I would introduce the concept that you already know. Like in this case, we're introducing conditional statements. And the first step is to translate that into something that is kind of not so structured and clunky. Okay, I'm just zooming out a little bit because I want to display both chunks of code on the screen like that. So you can see how the top version is typically what you would consider as structured code. Okay, and then the bottom one is not structured because if you look at the bottom one, it's got go-tos and labels. Okay, anything that has go-tos and labels really cannot be considered structural. But when you look at the execution, they're equivalent. Okay, because this one says if it is not true that if C is not true, go to label L1. And label L1 is skipping over block 1, which is the then block up here, right? So if C is actually true, then not C is going to be false. It's not going to go to L1. It will continue with block 1. And then after that, we have an unconditional branch around the else block to label L2. So these two chunks of code are basically functionally identical, except one is quote-unquote structured, and the other one is not. The lack of curly braces tells you that it is not structured anymore. Okay, we'll look at this again maybe on Monday next week. Pre-checking loops, same thing. While C do some kind of block 1, and the unstructured one, is having a label L1 to begin with, and then we check the condition. If the condition is false, then we get out of the loop. Okay, makes sense, right? Otherwise, if the condition is true, then the negation of the condition is false. We are not going to L2. Then we perform block 1, and then after block 1, we have a unconditional branch back to L1, which is at the beginning. So we check the condition again. So we keep doing that until the condition is true. Then, until the condition is false. Then not C is true. We go to label L2, and then that's how we exit the loop. So once again, the key is the curly braces are gone. It is not structured anymore. So these two are basically the most important control structures in C and C++, because a for loop is nothing more than a glorified while loop with initialization and then with the post operation kind of combined into the same syntax. So I'm not even bothering to talk about for loops. So the only thing left is a post-checking loop, which is a do-while loop. Do-while loops do not occur very frequently, okay? So because we're not dealing with a lot of code where the block itself is responsible for setting the condition C. That is the only time when the do-while block makes sense, is when you have to perform something that changes a condition, but if the condition is true, you want to perform that operation again. But that doesn't occur very often. Most of the time, we need to check the condition. If the condition is true, then we do something and then we go back and check again, which is a pre-checking loop. But regardless, once again, we're getting rid of the curly braces, and we're changing everything to use if and then a go to. Okay, so this is called, I call it flattening a C program. Okay, it's structured program that otherwise is kind of structured. It's not so structured anymore after this. And you can do this recursively. If you have a loop inside the conditional statement inside another loop, you can just apply this operation, at each level, so that in the end, there's no curly braces left. Okay, everything is done by if blah 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 go to. Okay, and you have lots of labels. Okay, and the idea behind that is when we get to the conditions, now we need to figure out, okay, what if there's a negation of some kind of condition? We want to get rid of negations, conjunctions, or disjunctions, so we'll be left with only comparisons, because we know how to compare, and we know how to use the result of comparing. So the key here is to get rid of operators. So C itself can be a complex expression. It can be a conjunction, can be a disjunction, and so on and so forth. Doesn't matter. This is step by step. Okay, so in this one, we get rid of a negation. In this one, we get rid of a disjunction. And in this one, we get rid of a conjunction. So there are structured methods to get rid of operators, just step by step until we end up with just comparisons. Then we know how to do comparisons already. Is that making any sense? So this is the stuff that we'll kind of focus on next Monday, not today. So today we'll just kind of come up with some code to do something that involves a loop and stuff. Yes?
Do we have class next Monday?
Yeah, spring break.
Oh, spring break. Ooh, okay.
Monday after next.
Party.
Okay, Monday after next. Next class.
Next.
We'll just say next class. Okay. I hate spring break. It's right in the middle of a semester. It just kind of it changes the momentum of the class. It just takes the momentum away, so that the Monday after that, I come back and then you guys would have forgotten what the condition is, what the flags are, what branching is about, what is a program counter, how to load the processor into Logicsim. But that's exactly why I have everything recorded, so I can make the assumption that you'll be watching that over the break.
So there's going to be a midterm on Monday?
The exam will be closed, so we'll have a practice exam right after the break. So that gives you a little bit of time to warm up again, and then the next week, the following week, we'll have the actual exam too.
So
I think that's fair. It's better than having the practice exam right before the break, and then the actual exam right after the break.
Yeah.
That would hurt. That would hurt.
That's painful.
That would be painful, yes. Okay, so this is what I want you guys to read over the break. So the Monday after the break, we'll start to talk about this stuff. So, but right now we'll just go ahead and write some code. Doesn't have to be very meaningful. It just has to do something so that we can have an example. So we'll go ahead and write a loop. Okay, so you guys get a choice. Do you want me to just write a loop, or do you want to see one step of that translation process?
Write the loop.
Write the loop, okay? Without using C construct. Or do you want me to write the loop with C construct so you can see how a C construct gets changed step by step into assembly code?
Yeah, I would like to see step.
Step by step? Okay, that makes sense. Okay. So we'll just assume that all the registers we only use the registers. We're not using any type of memory for this particular code. We'll do addition. How about that? We'll do addition. I mean, multiplication. We'll do multiplication by addition. Okay. 3 times 4 is the same as 3 times 3 times 3 times 3. Oops, plus. Okay. So we'll try to make a loop to do this. Okay. So how do you write a loop like this in C or C++? Okay. So we can make some assumptions. Okay. Do you want to use signed or unsigned integers? So are we multiplying signed numbers or unsigned numbers? Unsigned numbers are easier because you don't have to deal with negative values. Okay, so we'll say unsigned. So we'll basically say, unsigned A, B, C, D. And because A, B, C, D refer to registers, they do not need to be declared. They already exist. So as much as possible, I'll use C constructs to indicate that I'm just typing them. Okay, they already exist. Have you guys been introduced to the word extern in your C class?
No.
In some cases, yes. In some cases, no. Okay, so the word extern is basically saying we are not defining. We're defining the variables, but we're not allocating the storage. Okay, we're basically saying, okay, A, B, C, D already exists. We're just saying that, oh, okay, they are unsigned integers, but we are not allocating the storage doing this. So that allows you to share global variables between files in a C program, because you just need to have unsigned ABCD without the extern in one file, and then all of the other files can use extern unsigned ABCD to refer to that. Okay, so it's a really useful concept when you're dealing with projects with multiple source files, which unfortunately most of the time 360 does not get to because your programs do not usually require multiple files. But those are really important concepts when you go out to industry. Okay, and then we'll make some assumptions. We'll say, A is compute C equals A times B. Okay, so this is what we want to do. Okay, so the code to do it is, okay, we need to first initialize C to be 0. And then we'll say as long as A is non-zero, we'll do the following. What we need to do in the following is C plus equal to B, and then A is decremented by 1. That's it. That's multiplication by addition. Are there any questions about this code?
What do we do D with?
D is not needed.
Oh, we just
Yep.
add it.
It's just there, but it's not needed. Now, if you don't like this construct, this will trip all kinds of compile time error in Java, because Java doesn't understand or intentionally does not consider any non-zero values as false. Okay, so in Java you have to compare, okay, because you need to have something that returns a Boolean. So for those of you who unfortunately only know Java, this is the same thing as this. As long as A does not equal to 0, do the following, okay? But adding this is really helpful because now it becomes a comparison. And we know how to do comparison in this class, okay? So, are we good so far looking at the C code of what we want to do in today's lecture? Just the C code, okay. If that is okay, we'll first translate this, we'll flatten this program so that we don't have structure anymore. So the flattening is going to be, okay, we'll keep C equals 0, okay, but the while is going to be gone. So we have a loop here, or we have a condition. No, we have a label, sorry. So we have a label here. I'll just call this while begin, okay, because it marks the beginning of a while loop. And then the first thing we need to do is to say if A does not equal to 0, go to while end. Okay, I take it back. While if A does equal to 0, when we get to 0, get out of this loop. And then while end is at the end of this entire chunk of code. But we also need to know that there's an unconditional go to back to while begin right after the body of the loop itself. Is that making any sense? Are we still doing okay, or do we need to stop a little bit and
Could you explain
which part?
like while begin? This is the assembly language. Like
Nope, this is plain C. You can see you can make a label just like that too.
Oh really?
Yep.
Is that a variable or is that like pseudocode?
No, it is. No, this is real code. This code will compile as long as you have a variable A.
Oh.
It will
okay.
compile. This is actual C code.
Oh, okay.
Yeah. Well, you have to put it inside the function, but
Right,
yes,
right.
otherwise it does compile. Oh, so you guys will not introduce the go-to statement?
No.
Mm-mm.
Okay.
Or while begin.
Well, okay, so when I taught 360, I would introduce the concept, and then I would tell students do not use it, okay? Because it is useful in situations like this, okay? The concept is important, but it does encourage people to write code that is not structured, which is the reason why programmers, coders should not use it. So basically a go-to is like a jump, unconditional. It branches to whatever the label is and then continue execution at the label. That's all it does. But the go-to something is considered a statement. So this becomes the then statement of this conditional statement. Is that okay? Is that helping? Is that clarifying the concept, the construct? Okay. But it's also important to understand that not counting the body of the loop itself, this is the control structure. It sets up what condition we are checking, where are we supposed to go to exit the loop. At the end of the loop, it also is also setting up to go back to the beginning of the loop so that we can check the condition again. If the condition is false, then we get out of the loop. Otherwise, we perform another iteration. Is that okay? So the inside body, the inside part of this loop is still the same. So we have C plus equal B, A minus minus, just like that. So can we see how these two blocks of code are functionally equivalent, even though in syntax, they look different? Is that okay? The lack of indentation here is intentional because I want to show that everything is at the same level. Okay, indentation should be used only to indicate syntactic structure, and syntactically, everything is at the same level here. The labels, the go-to, the conditional statement, they're all at the same level, and this is why it's called flattening, because the structure is gone. Everything is now at the same level. Any questions about this part? We have not even gotten to the assembly language part. But trust me, the assembly programming part is going to be pretty easy for this one. Okay. So are we good? Okay. So now, when we look at this and we say, can we simplify this any further? Well, the only condition here does not involve a negation. It does not involve a conjunction. Does not involve a disjunction. So it is pretty much as simple as it can possibly get. Okay, so it's time to translate this into assembly code. To translate this into assembly code, it depends on how you would like to do things, but this is how I like to do it. Okay, so what I do is I would copy this to a new file. Okay, so I'm just thinking about which editor I should use. Let me do it this way. So I'm gonna save this file, and we'll save it into the temp folder. We'll call that molt.ttpasm, text toy processor assembly. And then I'm gonna switch editor, so we'll get rid of this guy, and then we'll use VI instead, because it's just a whole lot easier for me to use VI. Okay, so we go to the temp folder, and then we get back to molt. There we go. Okay, same stuff. So one particular reason why I like VI is it has a lot of features. Showing line numbers allows me to select which block of code to delete. So I'm going to delete everything from 1 to line 11 because those are kind of like steps to get to the actual code that we want to translate. So 1, 11 specifies a range, and then you can say what you want to do with the range, which is delete, and the whole block is gone. Now, this is even better. Now I can say substitute, dot means the current line, dollar means the end of file, the last line of the entire program. And then I want to substitute caret, which means the beginning of the line, with slash, and then the space. So what that does is to insert what we need to indicate this is comment, because remember, this code is intended as source code to the assembler. This is not going to go to a C compiler. Yes?
Can you do that command again?
Can we do it in?
On Vim, what you did in Vim right now to make it do the comments.
You go to the first line, or you say 1 comma $, at lowercase s for substitution, slash to begin the pattern that you're looking for, a caret to means the beginning of a line, another slash to end the string that you're looking for or the pattern you're looking for, backslash, slash, backslash, slash to specify the 2 actual slashes as the replacement, and then a space, and then another regular slash to end the replacement pattern, and then the potentially or optionally a G to specify multiple replacement per line. Yep.
Is this just regular expressions?
Yes.
Okay, cool.
Well, the only the caret is regular expression. The replacement string is really just literally slash slash. But since I'm using slash to separate the pattern I'm searching for and the replacement pattern, so that's why it has to be escaped using a backslash. Okay, but that is not the important part of this discussion. But you can see why I'd like to use VI because it has all of these features. Over time, you can, if you learn all of these things over time, it's actually going to be helpful. Okay, so C equals to 0 is easy. LDI would do that. Okay, it would clear the content of C, so it becomes 0. Label definitions. Guess what? We can we can uncomment these because the syntax is identical. And we're going to insert a halt statement as the last one so that the program can stop. So we can say, oh, okay, the program is done. And let's translate the easy ones first. C plus equal to B, that's an easy one. We can use an add instruction, and the order is the same. In other words, the assembly language that I invented intentionally follows the C convention of having the variable to be updated on the left-hand side, okay, and then the right-hand side is really just the expression that you're adding to whatever is on the left-hand side. A minus minus, there's a special instruction to do it. It's called decrement. So decrement is kind of cool because it's one single instruction. You don't have to load the constant of 1 into something first. And then we have a go to. Go to is just JMPI. Okay, I could have used the mnemonic of go to, but that would make the assembly code look too close to the C code. So JMPI or jump immediate is equivalent to go to. So JMPI to while begin. Okay, so now all that is left to do is this part here. Okay, so we want to compare A to 0, and if A does equal to 0, we want to go to while n. Unfortunately, the compare instruction can only compare between 2 registers. It cannot compare a register to a constant. There's just no pathway to do that. Okay, which is another whole discussion because one thing you can do is to look at the processor, and then you can ask yourselves. Okay, you can say, how come we don't have a CMPI instruction so we can directly compare register whatever out of A, B, C, D with a constant? Look at the look at the architecture itself. Look at the processor, how the multiplexers and demultiplexers are structured, and then ask the question: why is there not such an instruction? Is it because tech is too lazy to write that instruction, the microcode for that instruction, or is it actually just the processor architecture cannot support that instruction? Can you use a constant in RAM to feed to one of the inputs of the ALU? That is the question. And you will see that there's no such pathway possible with the current architecture. Okay, so that's an exercise for you guys to do. There's nothing to turn in, okay, but it is a puzzle. It is a suggested exercise so that you get more familiarized with the processor itself and you try to understand how to read the schematic of the processor. Okay, all right, so now we need to do LDI, okay, to another register. Register D is available, so we'll pick D here. So D is going to be initialized to 0 so that we can compare. So now we can compare A to D, which is the same thing as comparing A to 0. Now, because register D is not used anywhere else, you can actually move LDI D0 to outside of the loop so that you don't keep reinitializing register D. But I'm just going to keep it here, okay, because that is not really an important point. So after the compare, I'm looking for which flag to check for equality. we got 5 flags. We got C, which is looking for the minuend being less than the subtrahend unsigned. We have the sign flag, which is really just checking the most significant bit of the difference, which is not really helpful because in the case of overflow, it's going to lie. And the overflow flag is to tell whether the sign flag is lying or not. The L flag is to summarize the two, put those two together, and then basically it's saying, okay, is the minuend less than the subtrahend signed? Okay? And then we have the Z flag left. The Z flag is asking, is the result a 0? So which flag do you think we need to use in order to say, hey, if A is 0, let's get out?
Z flag.
The Z flag, very good. Okay, so we say JZI, jump if the Z flag is set to a particular label. Which label should we go to? Where should we go? While end, exactly, because it is equivalent. That's why I put these 3 lines of code, lines 5, 6, and 7, under the comment on line 4, because they implement the C construct on line 4. And that should be the entire program. Are we good so far? Yes? Okay. So if we think this is okay, then we'll go ahead and copy and paste it into the assembler. And for that, I need a different editor because.
So real quick,
yeah, go ahead.
The comparison, that's what set the Z flag set when we look for the JZI. That's using the Z flags already been set.
Correct. So this will change the Z flag according to the result of A minus D. This one is saying if and only if Z equals to 1, go to while end.
Otherwise, just continue with the loop. Okay.
Otherwise, it continues. Exactly.
Got it.
Yep. And that's why they implement what the C code is calling for here.
Right.
Except in the C code, you do not separate the comparison itself from the utilization of what you're checking for. It's combined into one. But in assembly, we have to break it apart and say, okay, what 2 things are we comparing? Okay, here's compare. And then you ask, what relation are we looking for? Are we looking for less than, greater than, blah, blah, blah? So that's why we have a JZI set from as a second step to utilize the flags set or cleared by the compare instruction. Is that okay? Now all of this discussion is going to be helpful in the lab activity tonight. So that means if you have any questions, okay, if you need time to write down anything, if you have any questions, this is a good time to ask. It might also be helpful, if you want to, to write down a timestamp, just so that you know at what time of the lecture recording we are talking about which concept. Yes?
So I know what the function of JZI is, but is it an acronym for something? I'm confused.
Jump if the Z flag is set. Immediate.
And the Z flag is from the ROM, right?
No, the Z flag is from the processor itself. Yeah. So when you look at the processor, the Z flag is in the flags register. But it is the flags register is nothing more than a register that remembers the flags that are set in the ALU. So when you look at the flags out here, the one that is labeled Z, which is this one, is coming from a NOR gate, which is all the way up here. And so Z is the result of a NOR of all the bits of the result of a calculation. So after a subtraction, if you have all the bits being ones, that means whatever you're comparing, whatever you were comparing, were the same. But the Z flag would be a 1 because when all the bits of the result are zeros, then you have 0 or 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 0, which means the result is going to be 0. But because the output is negated, so that means it's going to be. So the Z flag can be a 1 if and only if all the bits of the result are zeros.
So
yes.
when C minus 0 equals 0, jump to while end.
Yes.
That
is basically
sense.
what it's saying. Yep. Yep, that is exactly what it's saying. But in assembly code, we have to break it into 2 halves because we don't have one single instruction to do both the compare and specify which flag to use to do the branch. It is broken up into 2 steps. Do we have any other questions about this step? So this is good so far?
So
Yep,
if
go ahead.
the comparison flag had been set somewhere else, it had been cleared, right? And so if we try to use a JZ somewhere else in the program, it's going to use whatever the last flag was set, no matter how
That
far
is
back
correct.
it is.
Now there are only several instructions that will set certain flags. The Z flag can be set by almost every instruction that goes through the ALU, except for increment and decrement. Increment and decrement do not change the flags at all, by design. All of the other flags will change the Z flag, including bitwise OR, bitwise AND, right shift, addition, and subtraction, and bitwise NOT. They will all change the Z flag. And the reason is simple, because this is tapped out of the output of the multiplexer. In other words, we don't care about what operation we are choosing, because the select is only choosing which input becomes the output. Okay? But the Z flag is looking at the actual output of the ALU. So whatever the operation is going to change the Z flag. Except for increment and decrement, because they basically do not, with increment and decrement, they just do not enable the flags register. So that's why the flag register is not changed in a decrement or increment. Yep.
So just to clarify, D is serving the purpose as a register D is serving the purpose of
Zero.
as a constant. I can't talk today.
That's okay.
And it's just for comparing A to know when the counter ends, correct?
That is correct.
Okay, just wanted to double check.
Yep. The whole purpose of D is really just to store the constant that we're comparing to, because we cannot have a CMPI instruction. There's
Right.
just no pathway in the processor to do that. Yep. You good?
Answer my question.
Oh, okay, great. I like those questions. More than the other questions. Not that I do not like any questions. All right. So are we good to go, or are there any additional questions? Let's go back to the source code, and we'll stay here for a little bit until we are clear to go. I need to give you guys buttons. Oh, I need to give you guys an app, right? So I can see thumbs up and thumbs
give me
down
thumbs
and
up.
sideways thumbs. So if the thumbs up is at least 90%, then we actually go
Or we
forward.
just raise our actual thumbs.
Well, some
I like
people
the
may not
app,
feel
though.
comfortable doing that, right? So I have to be
But there's always
culturally
gonna
sensitive.
there's always gonna be that one troll who's just gonna slow down the whole always thumbs down.
I'll add a feature to ignore the troll, right?
After a certain
Ignore
number of
troll.
thumbs down.
The app will give me the ability to define what a troll is,
Yeah.
and then we have a troll filter. So, are we good? All right. So this is one of the things where it's not possible in an online class. So in an online class, I cannot gauge, can we move forward, or do we have to explain a little bit more? Which part do we need to explain more? Because with an online class, how do you do a lecture in online classes? So how is content delivered in an online class?
Spoon-fed?
Text, videos, but non-interactive, right? So if you don't understand something, then you need to send an email, and then within 24 hours, the professor will reply and ask for the clarification of your question. And then the next 24 hours will come back, with something else and so on. And that's why, a face-to-face class is different. Okay, so let's go ahead and do something about this. Okay, we're gonna exit, save it, and then we'll go ahead and I need to use mousepad, because mousepad is it's a GUI program. It allows me to do a Control A and a Control C, because the other one does not. So we'll go to the browser, we'll go to the assembler here. Okay.
You just gonna post the comments in?
Hmm?
You're just gonna paste
Oh
it?
yeah. The comments are totally recognized by the assembler.
Oh, cool.
Yep. By design. Yep. Go ahead. Question? Oh, I thought you had a question. Nope.
I got a quick
Oh,
question.
okay, go ahead.
You said the assembly code that you created, is there different kinds of like
Yeah, there are
assembly code?
variants. There are dialects of assembly code. So instead of using LD as the name of an instruction, some assembler can choose to use MOV, move, as the name of that instruction. Add is pretty standard. Decrement is pretty standard. JMPI is kind of my own because most assemblers would just use JMP without the I. But I already use JMP with a register, so so when you actually specify where to go to as a constant, I want to use a JMPI to differentiate it from just JMP.
Okay. So it's not like C that has like just a unified language, it varies?
No, it varies. Yep.
Okay.
There are definitely different dialects. Yep.
Huh.
Yep.
So just to be sure, halt is the same thing as end.
Yeah, halt is the same thing as, I think in C is more like exit 0.
Okay.
It really is just saying, okay, we're done, okay? But in C, when you're done, you can do a return from main, and then your program just exits, right? But in assembly, there's nothing to exit to. There's no operating system in the background. There's no command line. There's nothing other than what you're doing. So that's why there's no exit. And halt is just as good as it gets because it is an instruction that you cannot get out of. So from the perspective of tracking it, tracking the execution of a program, that is really important because you don't want to, unless you want to do a control T, control T, control T throughout the entire program. This gives you the ability to like zip through the whole program and then look at the log to figure out what the program did and did it do it correctly. So that's why we need a halt instruction at the end, because any memory space in RAM that is not initialized because there are no instructions that you specify, by default are zeros. And a 0 byte is equivalent to the no op instruction. So basically, if you do not specify a halt instruction, it is just like filling up the rest of the memory locations with no ops.
Okay, so you're
Which-
saying the rest
yeah.
of it is going to be zeros.
Right.
But it's
Correct, because when you reset the processor, RAM is automatically reset to 0. So, but the problem is by the time you get to location 255, 255, it rolls back to location 1 or location 0. So the whole thing starts from the beginning again. So you have no idea. It's really difficult to tell, have I reached the end of this program? Because if you don't end it with a halt, it just goes through and it goes all the way back to the beginning, and then the whole thing starts again. All right, so the program did assemble because I don't see any messages from column B. And then we can go to the RAM file tab, which has the actual program code. And you can see this program is not that long. I mean, in terms of bytes, we are counting, let's see, 2, 4, 6, 8, and then 1, 2, 3, 4. So we're talking about, what, 12 bytes or so? Okay, it's not a very long program. So we'll go to File, and then we click Download As. CSV or TSV would do, but I just usually pick a CSV, and I'll call it mult for multiplication. And then we switch back to the to Logisim so that we can start to run the program. And remember, one trick that I like to do is to type a Control R before you load anything into RAM, just to make sure that the processor is properly reset. The only thing that clicking this reset pin does not do is the clock itself. So if you left clock in the high state from the previous simulation, clicking that reset button doesn't change clock back to a low state, which is problematic.
I have a question.
Yeah.
When you hit Control R, is that using the logicism
Yes,
logic
it's
to reset it, or are you actually
It's Logisim doing
Are
it.
you actually triggering that reset?
It is not triggering this reset. It is actually having Logisim to reset the entire simulation.
Okay,
So,
so you're not using the simulation to reset it. Okay.
correct.
Kinda like pressing Control Y.
Hmm?
Control Y on Word.
Oh,
Is that a functioning reset though? I was just curious.
functioning reset.
You you have the reset set to when it's trapped. Can't talk today. tripped,
Okay.
and everything in RAM is reset to 0.
Right, that is this one is this button,
Right.
but it doesn't do the same thing
It doesn't do the same thing.
because the clock line cannot be reset by my own buttons.
Okay.
The clock line can only reset to 0 for sure,
Mhm.
using a control R, which resets the entire simulation.
Okay.
So everything is going to be 0 out when you type control R. Your RAM is going to be 0 out. All the registers will be 0'd out.
Okay.
Okay. Okay, so let's load the program in. Right click, go to load image, and then we go to the temp folder, and then look for molt.csv, and it's loaded in. You can see there are exactly 12 bytes here, and we can run the program. Okay, but right now it's going to multiply 0 to 0. Okay, because in the register bank, all the registers were reset. Nothing is programmed in. So we want to make it slightly interesting. Okay, so we want to do maybe a 3 times 4. Okay, so here's a 3, here's a 4. So we're expecting register C to end up with a value of 0C and not 12, because 1, 2 is 12 in decimal, but 1, 2 in hexadecimal is specifying 18, the value, the quantity of 18. So we have to understand that these are all hexadecimal digits and know what to expect here. Okay, so we can run the program. Just do a Control K to start clocking, and see how this is all getting changed. But if your program has a bug, and you're looking at this whole thing, when you do a Control T or when the clock is running, if you miss something, you're going to miss that something. Okay, you cannot go back in time and say, wait, hold on a second here. What just happened here? You cannot do that. So one way to debug a program is to use the log ability of the simulator. So you go to simulate, you go to logging. This is how you access log-related stuff. Okay, so this window allows you to pick what you want to log, and also other aspects of the logging of the stuff that is happening. Okay, so I'll go ahead and drag a few things over. Typically, you probably want to log activities in the PC, the program counter register, because that indicates the flow of your program in RAM. Okay, so PC is quote unquote equivalent to microcode pointer, but PC points to a location in RAM. The microcode pointer points to a location in ROM. The program counter points to opcodes, which you can specify in software, but the microcode pointer points to microcode slices that is in ROM that you as a coder, as a programmer, cannot have no control over. It is part of the chip. So is that clear? Which part is quote unquote software and which part is quote unquote not software? Basically, it's firmware or hardware. Okay, sometimes it's called firmware because it is updatable but not runtime updatable. It's like tofu. You got soft, firm, and hard. Hmm? Oh. And then with neural nets, now we have soy drink. Because it's even more fluid. How does it work? Where's the logic? There's no logic. There's no actual flow of logic. It's all neural nets. I've seen this before. I extract the pattern, so now I know how this works. That's neural nets.
Oh, Terminator, sir.
Exactly.
I think Terminator is too logical to be neural net driven.
Yeah.
Mm-hmm. That's in my humble opinion.
It sounds like you know.
No, I have no idea what that is.
Did you recently find an arm inside of a metal press recently? A metal arm?
Metal arm.
Terminator 1?
No, it's not metal.
Not metal? Oh god.
I do pass the Turing test. Okay, so you can add something to watch. Okay, so if you're familiar with the watch function in a debugger, let's say in CodeBlocks or even, I think Microsoft Visual Studio has that feature too. I cannot imagine any IDE not having a watch feature. Okay, so a watch feature is basically saying whenever the program counter is updated, create an entry of log, okay? But the entry of log includes everything that you're watching, not just the program counter, okay? So in addition to the program counter in this particular program, we also want to keep an eye on the registers, okay? Because we are adding stuff to register C, right? Register C is the product, and register A serves basically as a counter. So we want to keep track of those guys too. So then you can go to register bank, double click on the folder, and it will show you everything inside that is loggable. So everything that can be updated is basically loggable. So we want to keep track of register A, register B, and register C. Register D is kind of boring because A is just constant zero. Okay, so we don't have to track that. Let's see, we are not using any RAM locations in this case other than the opcodes. We're not using any variables in RAM. So that means we are not expecting anything in RAM to update. You can log those too, okay? But it's not going to show you anything that's interesting. If we understand the microcode enough to not to question the operation of the microcode, we don't have to log like the microcode pointer nor the ROM, okay? And there's just no need to do it. Yep.
What was the submenu that this was under?
This is under simulate.
Simulate. Okay.
Yep. So
Under
under
logging.
simulate, you go to logging.
Simulate logging. Okay.
Yep. Okay, so now you can also see that with each item that you're logging, you actually have control over the radix. Okay, that you are. Is it called radix or radix? Is it a short A sound or long A sound?
I think it's Radix, but I could be wrong.
I have no idea what it is. in the
Radix?
first place.
Radix? Okay. Okay, so the radix can be controlled. Whatever you select, you can click change radix, and you can go from base 2 to base 10, which typically is not very helpful. I personally would just go for base 16. So we'll change all of these to base 16, and you can reorder these things by using move up and move down. Oops. There you go. Too many clicks. There we go.
Oh, that's the number base. That
It's
you're
the
using
base,
as
so you-
octal or
Yeah, the problem with base 2 is they're really long, they're really lengthy, so I personally prefer to use base 16 because the assembler also output base 16 stuff. That really helps to kind of help you track all this stuff. Base 10 is just kind of awkward because there's no direct correspondence between base 10 and base 2. So in the event that you want to say, okay, what is the bit pattern of this thing, base 10 is not very helpful with that. So that's why base 16, combines the advantage of being compact and easy to translate into binary, and that's why most low-level programmers and low-level computer engineers prefer base 16 when
That
they look
makes
at
sense.
numbers. Okay, so that's what you can do with the select tab. Question?
It's radix when it's one radix, and it's radix when it's a plural.
Oh.
Radix.
Radix is for plural, and then
Yeah.
radix is for singular.
Yes.
Interesting. So instead of changing the end of the word, they changed the pronunciation. Interesting.
Dictionary.com told me.
Okay. Well, I have to trust that. Okay, so the table is currently empty because we haven't really done a single thing yet. So as we start click this thing, and we do not specify the log to a file, this will start to fill up with values, numbers, and whatnot. Okay. But I personally would not use a table because it's volatile. If you can only see it from here, you cannot use other tools to analyze your program. So that means we need to look at the third tab, and this tab I think is the best. Okay, because you can use the select button to specify a file name where the log is going to. Okay, any file name is fine. Okay, because the extension doesn't mean anything. So I'm just gonna name it as test.log. You can also name it as it also makes sense. Okay, I'll put it this way. It also makes sense to call it TSV because it is actually a tab separated file. So if you name it as a TSV, most spreadsheet programs will read it incorrectly and import all the data into a spreadsheet. And the advantage of importing into a spreadsheet is now you have all the tools, all the formulae in the spreadsheet to help you analyze the log. Okay, so I'm just going to call this test.csv for tab separated value. Click Save, and now you can see whether it is enabled or disabled. I would also include a header line. Basically, otherwise you cannot tell which column is which column. So it's kind of helpful to know that, oh, the first column is a program counter, the second column is register A, and so on. Especially when you start to track memory locations, because when you start to track memory locations, most likely than not, you will have to track like 4, 8 locations at a time, in addition to the program counter, the registers, and whatnot. So without the heading, it's really hard to know which column is what. Okay, so I would strongly recommend to include the header line in each row. Okay, so at this point you can close the window because we have now configured the logger. Okay, and now we can actually start to run the program at full speed. So we go to simulate, we go check the frequency. We can change it back to 4.1 kilohertz, which is as fast as it can possibly go. It's ludicrous speed. Okay, so now we can.
They've gone to plaid.
Yep, and now in Captain Picard's term, make it so, right? We can go, boom, and we are done. Okay, so getting out of warp. Everything is done. Okay, now this is the most important part. Your warp core is only good for one trip. After one session of using the log ability, it is time to close LogicSim because it has a bug. It corrupts something. Okay, I don't know exactly what it does, but the simulation doesn't work anymore after a log session.
Really? Even after Control R?
Even after, well, we can try. Okay, so we can try that later. Okay, but I'm just saying that if it doesn't work, if it doesn't seem to work anymore, it might be, it's likely because of the logging. So my personal preference is if I know something is going to be broken after something, I just assume that it's going to be broken and restart the software. Okay. All right. So now is a good time to say, what are we going to do with a TSV file then? Okay. So there are several things you can do. There are many things you can do with a CSV file. One thing you can do is to go to Google Sheets. Okay. Go pick a location. I can create one here, and I'll say new. Go to Google Sheets, and does it let me import something? No. Okay, that's fine. We'll create a blank sheet first. Okay, create and share. And I'll name this one too. So I'll name this one because it's already visible to all of you. So we'll go ahead and name it as there we go. As multiplication MULT log. Okay, multiplication log. And this is the really cool part. You go to File, you can import now. And import basically says, okay, we can do an upload, which specifies a file on the system itself, on the local computer. So now we can go to the temp folder, which we are in already. And then we can pick mult. Is it at the temp folder? Nope. Okay. So we have to go to the temp folder first. Okay, /cmp, and we pick test.tsv, and then we click open. So it will first upload the file, and it will ask you, okay, how do we import the content of this file? Creating a new spreadsheet, it's okay. We can just replace two because it's a blank sheet to begin with. Separator type, you can click tab because we know it is tab already, but you can also use detect automatically. Convert text to numbers and dates. It's kind of up to you. I would say no in most cases, especially when you start to use hexadecimal digits and binary numbers. It just doesn't convert well. So it's best to look at numbers as quote-unquote strings in that case. So I would pick no in this one, pick tab here, and just say replace current sheet. Okay, but it's all situational. Okay, it depends on what the spreadsheet looks like. Do you want to keep the old one, and so on and so forth. And you can click import data, and voila, now we have a spreadsheet with all the data that we have captured. Okay, I'm just resizing the columns, and so we can have more room to zoom in to look at the details. So what it's saying right here is when the program counter is 0, 0, we initialize register C. That's why it is logged, because register C, register C, it was quote unquote changed to a 0. Anytime there's a write operation to update something, even if the new value is the same as the old value, it triggers the log to create an entry. Okay, the first instruction that we have is LDI C, 0, which updates register C. That's why we have a log on row 2 of the spreadsheet. The second instruction at location 0, 1. Oh wait, that's not a new instruction, but we are changing the program counter, because the first instruction, the LDI instruction, takes 2 RAM locations. So the program counter has to increment to location 0, 1 to know what to use to update register C, and then register C actually gets updated. So nothing really shows anything that is interesting until we get to this one here. This is when we can see that, register C is incremented by 4. So the question is, are we at the right instruction? The location, okay, where do you think is the location of this instruction that updated register C from 00 to 04? Where is it? Which column do you look at to find out which instruction is responsible for this? The PC, the program counter. Okay, so the program counter says we were at location 08 when this happened. So now is a good time to go back to the source code. So we go back to the assembler tab, the assembler spreadsheet. And I made one special tab called source debug, which gives you the lines, the original source code, and also the location in column C in hexadecimal for that specific purpose. So when you look down to location 8 is the decrement instruction, but remember, the program counter is auto incremented at the decode phase. So that means by the time the instruction executes, the program counter is already 1 more than what it should be. So when you see the program counter as 08, the actual instruction that is responsible for any changes to the registers is 07. So when you look up 07, it is indeed the add instruction. We're adding register C to we are adding register B to register C. Okay. Well, is the log actually saying that? The log is saying that, okay, this is register B, this is register C, and if you look at the change of register C, it does seem like we just added the content of B to C. Okay. And then when you track down a little bit more, basically you're looking for lines that reflects changes. Yep, go ahead.
Why are there 2 number 8s? Is that second 8 just showing the change?
There are 2 8s because the first one is triggered by a change of the program counter. The second one is triggered by the change to register C.
Gotcha.
So anytime any component that you're watching has a change, has an update, it generates a new row in the log.
Okay.
So that's why it is, sometimes you look at a lot of things and it's like, okay, this is of no interest. It's perfectly okay. And you're looking for changes of either memory locations or registers other than the program counter. All right, so, and as we go, we can see that, register, this is another trick you can do with any spreadsheet, not just Google Sheets. You can move this tab down a little bit. It breaks the screen into 2 halves so that you can scroll on one half while the other half stays stationary, which can come in pretty handy like now. Okay, so you can see how register A changed from 03 to 02 at this point. The location of the instruction that is responsible looks like it's 09, but remember, by the time we get to the part that it changes the registers, the program counter has already auto-incremented, which means you have to back up one location and say, oh, okay, the instruction that is responsible for changing register A from 03 to 02 is 09 minus 1, which is location 08. So now you can go back to the other sheet and say, what is at location 08? At location 08, we have a decrement instruction. Okay, seems to make sense. Decrement A went from 3 to 2. It's all good. Okay? So you can kind of analyze a program like this, but if you analyze a program like this, it can take you a long time, especially when you have some long loops. Okay? Like if I say, what is 1,000 times 1? Okay, this is going to keep going and going and going for a while. We cannot specify 1,000 by the way, because the constant or a register only has 8 bits. So 255 is the best we can do. Okay, but let's say you're saying, okay, I know this loop is working. I just want to see how it got out of the loop. Okay, so how do you look at the trace or the log and find out how it got out of the loop? In other words, how do we get here? How do we get to line 15 of the program, which has a location of 0B?
It grew sentient.
Hmm?
It grew sentient.
Check the logs.
We can check the log,
For when
but
it
how do you check the
transfers
log? The log is very long and is really tedious,
Control F.
but it does have features. Okay, so in the log here, you can click on the column, and then you can go to edit, and you say find, and optionally replace, I think. Can we just find and not replace?
Control F.
Control F. Control F is the search of a browser, which doesn't work in a. Oh, okay. Okay, I see. It's in the cheat. Okay, good. But it's not in the edit menu. Is it in one of the other menus?
I have no idea.
Okay. So Google Sheet is basically hijacking Control F, so Control F can no longer do a in-browser search or on-page search, which makes sense. Okay, so we're looking for 0B. Oh, are we looking at 0B? Remember, by the time we get to the halt
The
instruction,
one after it, right?
well, but it has to increment from B. It has to increment to 0B first. But when it increments to 0B, we will be in the previous instruction, which is probably which instruction? What instruction is right before the halt instruction? Not sequentially, not when you look at the listing, but logically when you run the program, which instruction is immediately before the halt instruction?
A comparison?
No, you're close.
Go
What
to-
happens right after the compare?
Go to.
The branch, the conditional branch. The conditional branch should be the instruction right before, okay? But, looking at 0B is not a bad idea. But we also want to look at 0B in column A. Let me see if I can specify that. So we're looking for 0B, and can we specify that we are only in column A? Match entire cell content, new. So we can select first. Okay, so let's try that. Select the whole column, Control F, and then look for 0B. Oh, it looks right away. It's like instantaneous. Okay. So that is 0B. So this row is significant because this is the time when the program counter changed from 06 all the way to 0B. Okay, it has to be a branch instruction, because otherwise the program counter would only increment. Even when you have instructions that have multiple bytes, the program counter still only increments. It doesn't skip, because it has to increment to the second byte of an instruction. So you will still see the program counter just being added by 1. The only time you can see something that is skipping like this has got to be a branch instruction. So now I'm saying that 06 is most likely corresponding to the location that is the second byte of the conditional branch instruction, not the first. So the first byte would be at location 05. Okay? Do you guys remember how the conditional branch, the JCI instructions work? The program counter is already incremented right after the opcode itself. Okay, but so it has two choices to update itself. It can either increment one more time to continue when the condition is false, or it can load something that the program counter itself is pointing to back into the program counter to perform the actual branch. Okay, so 06 is the location that specifies 0B as a destination location, which means the opcode corresponding to the conditional branch is 1 byte before 06, which is 05. Okay, so let's check. Okay, I can yak all day long, and but we can now say, where's my conditional branch? It is here, and it is indeed at location 05. It starts at location 05, but it takes 2 bytes. So location 05 and location 06 are both specifying the conditional branch instruction of JZI. Yep.
How can you tell that it takes 2 bytes?
Because anything that ends with an I takes up 2 bytes.
What's that?
Because the immediate operand takes 1 more byte.
Oh, okay.
Yep. Is that okay? But this is how you kind of check your code and see whether it works or not. Okay, is to look at the trace. You go back to the source. Okay, there's a source. There's source debug, which is kind of like a quick summary of which location had which original line of code, which makes it easier for you guys to look at the location and be able to get back to what opcode we are talking about. So at that point, the program would have finished already, and you can see how register C already has the product between register A and register B. Because register A had a value of 3. 3 times 4 is 12 in decimal, but 12 in decimal is 0C in hexadecimal. But the next question is, did the program terminate? Did it stop? So we keep going, and you can see that, by the time we get to location 0C, by the time program counter get to location 0C, the whole thing stops. And by the way, this location 0C has absolutely nothing to do with what value is in register C. Oh, I can see that, no pun intended. At location C, or when the program counter is at location C, register C has a value of 0C. But they are all completely coincidental. So are we okay so far? So if the program stops here and there's no more log past this point, where is the halt instruction?
0B.
It would have decoded and executed the halt instruction by now. The auto increment of the program counter is at the decode phase. So this 0C in the program counter is post increment already. So that means the location of the halt instruction is at 0B. Okay? And we can double check. Go back to the assembler spreadsheet and look at the halt instruction. It is at location 0B. So this is how you can run the program and look at the result and analyze what happened during the execution of the program. And if your program has a bug, this is how you find your bugs. There are no printfs, there are no couts, there's no way to set breakpoints. This is the tool. Okay? And you guys may think that, hey, this is extreme. This is not what I signed up for. Okay? This is not what software is about. Well, in the past, this is how you do it. I used to be an embedded system software engineer. Okay? And an embedded system is basically a circuit board about this big. And this is back in the time when we still have external ROM and external RAM, to the processor. And the way to debug a program that is on those things, there are no debuggers. Okay, there are no debuggers to hook up to it. The processor was too simple. It did not have any way to be debugged using GDB or anything like that. When you're writing the firmware, which means there's nothing before you. There's no operating system before you. There's nothing before you. So to write the firmware, you're really kind of like flying in the blind, in the dark, because you can't really see, there's no way to visualize the execution of the program. But fortunately, we have such a thing called a logic analyzer. Have you guys seen a logic analyzer?
I think you introduced it to us previously.
Did I?
Yeah.
Okay.
This class.
Yeah, these are modern logic analyzers where they're just a USB thing that you hook up to something. So we want to look at a logic analyzer back in 1980 and see if we can dig up some images of those things. No, these are,
Pictures from a museum.
because I used to work with these things. They have a lot of connections. Nope. Yeah. They have probes like this, so you basically have ways to clip onto every single bit on the data bus, every single bit on the address bus, every single control wire, like write versus read, all the select pins, la 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 la, and then you hook up everything into what we call a logic analyzer. So as your program executes, there will be bus activities that are visible from the circuit board itself, and that will be captured by the logic analyzer. The logic analyzer will then need a module installed so that it can disassemble from the trace of electrical activities. It can disassemble what instructions executed with the addresses and so on and so forth. That is how you debug a program back in those days, if you could afford a logic analyzer. In 1990, a used logic analyzer that is probably a lower end version of the entire product line was about $10,000.
In today's money or 1990 money?
That's $1990. Okay,
Oh, wow.
$1990, 10,000 of those. Okay, so they were pretty expensive, so a lot of times companies that cannot do it, they just have the circuitry that hook up to an LED, and whether your program got to a certain point or not is whether the LED is lit or not. And you use that to debug your program. So having the log ability and being able to import it into a spreadsheet so you can use spreadsheet functions to analyze that is already a big help. So, do we have any questions about what I just did today? The program itself, the process that I went through to create the log, or the analysis of the log itself? Because there are those three distinct phases. First, we got the C program. We translate that into assembly code. We put the assembly code through the assembler. We got the actual code of the program. And then we ran it in the simulator, but we collect a log file as a result of that. And then we analyze the log file to say, okay, did it work? Did we multiply register A to register B to get the result in register C? How did we exit the loop? How do I know that whether it exited the loop or not? So are there any questions about those specific steps or concepts? Because your lab activity is going to need those. Is that okay? No questions? All right.
Not until we get there.
Not until we get there, that's right.
Yep. Okay. Well said. Okay. Okay. So I'm gonna stop the log, and then we can stroll over because we have. I'm ending the class about 5 minutes earlier.
Oh wow.
Do not ask for a refund. I will just have 5 more minutes next time after the break to make up for
We already
it.
have a backlog.
Hmm?
You owe us time.
I don't think.